Okay, first of all, I'd like to thank the Isaac Newton Institute and the organizers of the program for giving me the opportunity to speak here. I'm going to tell you a little bit about some ongoing work that's been done in collaboration with Gabriel Lopez Cardoso and Suresh Nampuri. And basically, it's going to deal with taking first steps towards applying machine learning to construct integrable models or integral deformations. And basically, my talk is organized as follows. So first, I'll give a brief, kind of redundant introduction after all the talks that we have had in the last days about what we want to achieve in this field. Then I'm going to speak a bit about the deformations of integrable models in 2D, which have been dealt, for instance, in the previous talk, and also in Christina's talk. Then I'm going to restrict a subclass of those models that actually allows for a one-dimensional description. And it is for those one-dimensional models that I'm going to talk a little bit about the machine learning aspects. And finally, then I'll give my conclusions. So, of course, is a central theme of research in classical gravity is about characterizing the solution space. And it is a hard problem, as Christina was highlighting, because we're dealing with nonlinear partial differential equations. Then, let's say within the last 50 years, some techniques on some solution generating methods have been developed. And those methods basically have symmetry as a common motive. So starting from Backlund transformations, the lax pair constructions of Belinsky and Sakharov, and then the mostly discussed linear system within this workshop, the Breitenlohner-Maison linear system that was introduced in Gabriel's lecture last Friday and has been also approached by Gianluca, Christina, and many others. So we know that a subclass of this four-dimensional solution is integrable, and the naive idea of integrability is that it's characterized by an infinite tower of conserved currents. And the operational definition of integrability for this talk and for many of the talks that we had so far is the definition by ITS. So essentially that integrability implies the existence of a linear system that provide us with the equations of motion for the system as some compatibility conditions. And essentially we'll be restricting to 4D stationary axisymmetric solutions of gravity coupled to matter. And provided that the system has two isometries, then we can view this system in 2 dimensions. And at the 2 derivative level, as Robert was mentioning, we know that the system is integrable in the absence of a cosmological constant or a flux potential. So our goal is to study the integrability in the presence of such cosmological constant or flux potential. So basically, we deal with Einstein-Maxwell spaces in 4 dimensions with a cosmological constant or a flux potential. And the question that is part of a program that started almost 20 years ago is basically if we can define integrability in this case by constructing a deformation of the Breitenlohner-Maison linear system in the presence of a cosmological constant, right? And some results have been obtained by other approaches, and the conclusion, something that we're gonna also arrive here, is that I mean, there's some sense of partial integrability for these deformed models or models in presence of the cosmological constant. So for the 2-dimensional system, as I mentioned, we are going to consider the deformations of the BM linear system in the presence of a 4-dimensional potential. And of course, then now there's an entire program that has to be developed in terms of looking for solutions. In Thomas' talk, he highlighted the importance of maybe looking for machine learning techniques that could help in this endeavor. And for this talk, basically, we're going to consider a subclass of solutions for which the problem can be reduced to a one-dimensional system. For this one-dimensional system, we're going to see that there is actually a Hamiltonian description, and this connects our problem with some efforts that have been taken already in constructing lax pairs in one-dimensional systems. So if we look for the two-dimensional model, as I mentioned, let's start in 4 dimensions. Take Einstein-Maxwell gravity coupled to a bunch of neutral scalars for which there is a 4-dimensional potential term. And then if I want to look at the metric, that's the solution, the classical solution I'm looking for, the solution line element is going to take this form, or we're going to consider solutions of this particular form. So basically, here these deltas that appear also in Christina's talks, where our warp factors, the B is basically the B field we're going to set to 0, and then we have additionally this field sigma and this field rho tilde that's going to be the dilatron. So basically, we want to find the equations of motions for those fields entering the actual target space metric. So in the presence of the two isometries, we can perform a 2-dimensional reduction, and this is a special 2D reduction. So first, we reduce along the t direction. So basically, we end up with a 3-dimensional metric, Euclidean. Then for this 3-dimensional model, we can Hodge dualize the two forms of the theory, and then we end up with a 3-dimensional nonlinear sigma model that, for our purposes, we're going to view as a coset model. And then we reduce along a second isometry, the isometry phi here, and then we end up with a 2-dimensional system with basically coordinates rho and b, right? So the corresponding 2-dimensional action now it takes this particular form. So basically, this rho tilde plays the role of, I mean, if you look at it kind of as a comparison with Roberts, this is basically the R that he had in his action, and there is a gauge field, a U1 gauge field, and then these are the kinetic terms for rho tilde and sigma, and then this is the potential term that descends to 2 dimensions from a 4-dimensional potential term, and these are, of course, warpings that you pick up from the 4-dimensional reduction. Since we are considering a coset model, then we can write the field A in this particular form in terms of a matrix M that is in the coset. So now we have to find the equation. Well, I mean, you can look for the equations of motion for A, rho tilde, and sigma, and then you're going to pick them up from essentially variations of the Lagrangian that I just mentioned. And then basically we're going to divide the equations of motion into 2 classes. So the first one involves the gauge field A, and basically is going to be equal to some function g that is going to depend on the 4-dimensional potential. Then you would have the equation of motion for rho tilde, that in the absence of a potential is 0. And furthermore, you would get the equations of motion for the field sigma that we're going to denote as consistency conditions for a reason that's going to become clear in a moment. So if we look at the absence systems in which there's no cosmological constant or no scalar potential, then the first 2 equations of motion are going to take this simple form. They also appeared in Christina's in the same notation. And then basically the box rho tilde equals to 0 equation implies that rho tilde has a harmonic dual. And then this bile coordinate that we have in the 2-dimensional metric can essentially be replaced, can essentially be replaced by rho tilde and b tilde. Similarly, we consider very special simple systems for which the rho tilde essentially factorize the expression for rho tilde, the solutions for rho tilde essentially split into a term that depends only on the coordinate rho and a term that depends only on alpha on a function of the coordinate b. So the linear system basically is described by these 2 operators that, acting on the solution, give me a 0, and this can be written in this particular form. Tau is the spectral parameter that we have seen already, and omega is the spectral curve. So, and the lesson to take from this slide is that the compatibility condition for L and M, which reads as the commutator of L and M acting on X equals to 0, is going to imply equation 1. And since we have this freedom to pick rho as rho tilde, then the box rho tilde equation basically is satisfied automatically. In the presence of the cosmological constant, basically now we're going to assume a very special type of solutions. So basically, this is our metric again. We have set B to 0. And if we assume that delta and sigma depend only on the radial coordinates, so to say rho, then, and also that the gauge field depends only on rho and it's only along the rho direction, then we get these equations of motion with a similar condition as the one we had before. So in this case, now rho tilde, the dilaton, is now written as a product of these two functions. And basically, we're going to distinguish two cases. The first case is a case in which rho tilde depends only on the coordinate rho. Then the system is truly one-dimensional. And the second case is manifesting some spherical symmetry. And therefore, we take alpha b equals sine of b. So for these two cases, the equations of motion that I started with can be rewritten in terms of basically h of rho, h, a rho, and sigma, and then they take this particular form. So again, the two equations, the two main equations that we're going to deal with are these two. Are this, yeah, exactly. So basically, a rho, this is the equation for a rho, and again, this is proportional to g, that is some function of the potential. Similarly, the box equation for rho tilde is this one that now is, of course, non-zero. And then to distinguish the two cases, basically we have these constants a and c, that in the first case, for alpha being a constant or being equals to 1 is equals to 0. So basically this becomes just a second derivative here. And alpha can take suitable real values. And the spherical case, C is going to be equal to 1 and A is going to be equals to 0. So in the B equal to 0 case, so no potential, the Lax pair for a system on which only a rho is non-zero is given in this particular form. So now we are going to look for a deformation of this Lax pair that provides us with the equations of motions that we have now in terms of the potential. So basically, the deformation that we're going to introduce is by means of a function f of rho. So remember that besides rho tilde, everything depends only on this radial coordinate rho. And then f of rho, we find to take this particular form. And the idea is that as I switch off the potential, that is basically going to be described by this function g of rho, then I get back to the undeformed linear system that I had in the beginning. So basically, you can easily see that if H0 was defined as the radial component of the dilaton in the no potential case, and then H0 becomes, so H becomes H0 as B becomes 0, and therefore you can check, obviously, that f of rho becomes 0 in that limit. So we recover the undeformed Lax pair in that case. So furthermore, the deformation was chosen in such a way that the compatibility condition for the Lax operators or the linear system operators implies the first equation of motion. But in general, we have to separately solve for rho tilde because in this case, of course, box rho tilde is non-zero. And therefore, the linear system will not tell us any information about the dilaton rho tilde. So the philosophy or the lesson, if you wish, from taking a cosmological constant while demanding that you have a Breitenlohner-Maison linear system is that you can recover now a subset of the equations of motion that you otherwise have recovered completely in the case of zero cosmological constant. So exactly. So basically, then you can solve. So the other conditions that you had were further consistency conditions that you can check that they are indeed satisfied. And then the resultant linear system, written in a more convenient form, is given in this particular structure. So, okay. Yeah. So the next question, of course, is you have some partial integrability. You should expect to be able to construct some sets of conserved currents. And basically, if you have a solution, sigma for sigma, rho tilde, a rho, etc., then you can solve for x that solve. I mean, you can solve for the x that solves the linear system. And then you can use that x to actually find some currents, no? And this particular current was introduced in this famous paper by Nicolai. So once you have a solution, then you compute this object. Of course, if you take start of D of this object, then basically you're going to get a conserved quantity. And then you can take now an infinite, well, I mean, a power series expansion in 1 over the complex parameter omega. And what you get is basically this infinite series of currents that are, of course, subject to this conservation law. So the lesson to take from here is that, of course, now that we have introduced a deformation, we'd have to look for a solution in order to check that indeed we have the conserved currents, right? So at this stage, what our approach has achieved is to enable us to construct a wide class of solutions, if you wish, that are of physical interest. So if you take the case alpha equals sine v, this is case 2, we would be dealing with static spherically symmetric black holes in ADS4. And if you look at alpha equals to 1, then we'll be dealing with domain wall solutions. This is one of the solutions that we obtained. Basically, this is Einstein gravity in the presence of the cosmological constant, applying some of the nice techniques, Sabina-Hopf factorizations that Christina introduced nicely this morning. Then we'll be able to get some solution for X and check that indeed this solves the linear system, the kind of deformed linear system. And for that, we'll be able to construct then the explicit currents in this case. So, of course, there is further work that needs to be done in order to obtain more and more solutions in the presence of cosmological constant of flux or flux potentials. But let me just keep this kind of discussion until here. And now let me switch gears to another possible version of this story that would take us to the one-dimensional picture that I'll also want to discuss with you. So these four-dimensional gravitational models that we were considering seem to have a close relation with one dimensions, basically everything dependent on the radial coordinate. And then one can think that basically these 4D models coupled to U1 gauge fields, neutral scalars, subject to a scalar flux potential, can be viewed now as a one-dimensional model. And the approach is now to take the sphere reductions to 2 dimensions, and then we integrate our time. So we are left with this type of one-dimensional actions that basically take now fields u and psi. Basically, u was related to the warp factor delta, and psi is going to be related to this field sigma that we saw appearing in our four-dimensional line element. Then we can add additional scalars, xi's, and then this would be some sort of kinetic term. We can allow for electric and magnetic charges, and then we're going to pick terms of this particular form. And this guy over here is going to be the flux or the scalar potential that would be related to a four-dimensional one. So this just to show that indeed this subclass of four-dimensional solutions admit also a one-dimensional description. And then for the 1D models that have been studied for a long time already, then the question is if we can write now a one-dimensional Lax system. So the simplest example that we can think of is of basically no scalars and just a U1 and a flux potential. So we had this, we have rotated all the charges, and basically these are the terms that appear. So this flux is H0, and then you can see that basically the system decouples for H equals to 0. So basically everything becomes integrable, and then, well, that would mean that we can write a Lax pair for the H0 equals to 0 case without much difficulty. So the aim is to construct Lax pairs, but the Lax pairs here we're going to see basically as matrices that depend on the phase space entries, so to say. So basically, if we look back our action, we're going to see that, I mean, we want the Lax pair to depend on U prime, psi prime, U, and psi. And if we have a Lax pair, if we can construct a Lax pair, then it allows us to construct the tower of conserved current as traces of powers of the operator or the matrix L. So now if you view integrability in the sense of you will, then we need further that these currents or these conserved quantities that we have constructed are in involution, and then there is a beautiful connection to the R matrices. So basically, if I enlarge the, well, I mean, take the tensor of vector spaces on which L acts, then taking a single Lax pair, I can build now two Lax operators, and then basically I need to satisfy this relation for a matrix. And then the idea is that this matrix R12 or this R matrix indeed exists. And these type of problems have been shown to be amenable to machine learning. So basically, what we want to achieve here is the construction of Lax pairs aided by AI, by neural networks. And the type of models that we are considering are basically following into a category of what's essentially known as PINs, or physics-informed neural networks. And basically, what our neural network is going to do is to take phase space elements, whatever I have in my action or my Lagrangian, and then for these guys, it is going to produce a pair L and M, two matrices or a given dimension, depending on what do I have in my phase space. And then the minimization of a given loss must lead to a pair L and M that indeed satisfies this Lax pair equation. So, of course, if I look at this kind of thing, I will see that I have to take derivatives now of L on T, and then the simplest way to do it is through the chain rule. So basically, I get derivatives of L and M, well, I mean, in this case, only on L, on the phase space inputs, and then I take the scalar product with the equations of motion, so to say. So in addition to the phase space, I am going to have to compute the equations of motion, but these derivatives of outputs from inputs in a neural network has been, well, widely discussed in Sven's talk, and this follows to what's known as automatic differentiation. So we are gonna deal with what is known as a feed-forward network, and basically this is an array of various layers, and each layer is going to have a different number of neurons, and the neurons, or these perceptrons, are basically, as Shailesh was mentioning, going to emulate what one expect with an actual biological neuron. So you take some inputs, some stimulus, and basically you're going to weight these inputs by some factor W, and then you could add some biases. And then depending on what this value is, you're going to expect some nonlinear reaction. So basically, this neuron is going to decide whether it fires or not. And the sigma here, or the response, is going to be modeled by what is known as the activation function. And there are various activation functions to pick from. So the most common one is the ReLU. But as you see here, this is not so useful if you want to take derivatives, because it's, of course, having problems at zero. So we're going to deal with things like hyperbolic tangent or sigmoids, as they are better behaved for our purposes. So basically, in this feed-forward neural network, we take an input layer. So this dimensionality is not the one that applies for our problem. This is just schematic. But basically, whatever information comes here, then is sent. All the neurons are connected from layer to layer, and ultimately I am going to get an output that, in our case, are going to be the entries of the lax pair, of the lax matrices L and M. So this is not such a trivial problem, because the lax matrices are not unique. They are not guaranteed to be there. You have to really look for them. And there are many symmetries involved in this problem. So for instance, you can rescale L by a coefficient, and then this is also a lax pair. Or you can take a known lax pair L and M, apply a GLNR transformation, and then we get a new lax pair system for these guys. So there is a lot of freedom in the problem. And ideally, what we would like to put in the laws are quantities that are invariant of all these redundancies. So that, I mean, we help our neural network to get to the solution that we actually want, no? So something that is observed in this system is that for most of them, this is not definite, but for this one-dimensional system, you can see that the lax pairs that are known kind of find the Hamiltonian at level 2, and at level 2 in L. And then one could think that a way to get rid of this annoying scaling over here is to construct a loss that takes the trace of whatever L matrix I get out of the neural network and make it match the Hamiltonian. So this is also helpful, because a trivial solution to the lax pair is one where the matrix L is equals to 0. So, of course, this doesn't know anything about the lax pair equation, and then I have to find ways to introduce this, right? So I could take, for instance, a loss that takes every single component of this equation and squares it, so that it's going to minimize this quantity. But if I want to amplify this difference, I could take, for instance, exponentials of the left at the right-hand side, or basically this is the same as an exponential of this quantity over here. And then in this case, I'm going to look for the deviations from 1. And this seems to work much better, because of course it's more sensible to these differences in solving the lax pair equation. And then the total loss is going to be a weighted sum of all the losses that I could come up to kind of drive my learning process towards a neural network that, or towards a result that is essentially satisfactory. So of course, you are doing machine learning, you need data. And we could look at the phase space and consider, for instance, a box of radius 1 or radius 2, and sample random points from this box, then compute the equations of motion that you know from your Lagrangian. And then we're going to sample between 100,000 to 1 million points. And these are going to be the data that we're going to train. Let me remind you that this is not a supervised process in the sense that I don't know what the output is. I'm going to find the output through a minimization of a particular loss. And this is what I was mentioning. So basically, you can compute the LDT by a chain rule involving the equations of motion. And for our experiments, we have split the data 80% for training and 20% for validation. The networks that we have found to work relatively okay in these kind of experiments are neural networks with 3 hidden layers, with tangent activation function, and our implementation was done in TensorFlow. So as a warm-up, let me show you a much simpler system. So basically, we can take this one particle Hamiltonian that is described basically by the kinetic term plus a potential, and then we can look at different potentials and see what happens. So basically, these type of exponential potentials are known as Liouville models. If you take a harmonic oscillator and 1 over q squared term together, these are a family known as D'Alfaro-Fubini-Furlan models. Or you can take something linear and whatever crazy things you want to play with. So this is essentially the training process for each of these guys. So you see that basically we can get losses dropping down to roughly 10 to the minus 7 or 10 to the minus 6. And basically that's the kind of training that we do. So just to show you what kind of things do we obtain for these very, very simplistic examples. So if you look here, the phase space is 2-dimensional. So basically, I'm evaluating now on 3 different phase space points. So these are the values for L. So the L matrices that I get out of the neural network. And these are the values for M. And if I want to check how do this L and M produce or how far are them from satisfying exactly the Lax-Spare equation, then you see that for every entry, we're going to have roughly 10 to the minus 4 or 10 to the minus 3. So now this is not something that is entirely satisfactory, because ultimately you would like to get close expression for your Lax-Spare. You would like to know that, I mean, indeed, you can find something that is actually 0. And then you'd like to know what kind of functions enter into these entries in these L matrices. But so just as a starting point of something that we are exploring, let me show you how do these entries look like some of these entries look like in this phase space that we have picked. So if you look at the L11 component, so these components over here, you're going to see that basically they seem to depend up to a tilting only on the coordinate P. So basically P goes into the diagonal. And if you look at the off-diagonal component, you see exactly the opposite thing. So you tend to align Qs or Q-dependent functions on the off-diagonal pieces, and actually P's or functions of P on the diagonal. So basically this could help you to start building some Lax-Spares. So something that we also notice here is that, for instance, if you look at the M matrices, you see that this component over here is roughly 1 order of magnitude bigger than all the others. So it seems that these kind of solutions that we are finding for the Liouville model or for these one particle, 1-dimensional models go towards this kind of analytic expressions. So basically an M that is only excited in this direction, and then basically P or P-dependent functions in the diagonal, and then something depending on Q in the off-diagonal pieces. Of course, this is partly playing with the neural network and partly knowing what kind of lax pairs are expected in these systems. And therefore, it will be very important if you are dealing with more complicated models like the ones that we want to explore, to see if some techniques that would get us some close expressions for the components of the L matrices and M matrices are actually feasible. So, of course, we can play a little bit with our Einstein gravity model with a U1 and a flux potential. And then, as I was mentioning, if I set H to 0, then I know how to build a lax pair for these guys. So basically, our hypothesis here, I mean, this is not guaranteed, but we are going to assume that, again, we find the Hamiltonian at level 2 in L, that now, since we have 2 degrees of freedom, that our lax matrices are not going to be 2 by 2 anymore, by 4 by 4, and that whenever it's possible, we'll be able to use these one-dimensional kind of building blocks that we just saw in order to get our actual lax pair. So if I set H equals to 0 and I train for a model, then basically I can again go to roughly 10 to the minus 6, 10 to the minus 7. I mentioned that if now I have H0 non-equal to 0, I could look now for Q equals to 0. And even though it looks very innocent, after trying a few hours, you'll see that it's not so easy. Well, I mean, we haven't been able to do it so far. Please, if you are interested, let me know. But we haven't been able to find an analytic expression for lax pair in this case. And somehow, if you wish, the machine is kind of telling you also that this problem is more difficult than the one you are approaching. So basically, if you initialize your neural network at random values, the difference or the loss that you start with here in the known case is roughly 10 to the minus 1. You saw it there also at the one-dimensional or one-particle systems. But here you start at 10 to the 3. No? And if you don't have now a Q0 or H0 set to 0, then you start with losses of order 10 to the 4. You can still go down, but then the question is if these models that basically are losses in the order of 10 to the minus 5, 10 to the minus 6, sort of really capture the entire story and tell you that indeed you have a lax pair for those systems. If the entire picture is patching together nicely and the 2-dimensional story and the Breitenlohner-Maison linear system indeed shows that there's some integrability in these models, then the one-dimensional version should be able to give you some one-dimensional version of integrability as well. And of course, as I mentioned, telling somebody who has worked with these kind of things that you get a lax pair up to order 10 to the minus 5 or 10 to the minus 7 is not sufficient. So there's more work to be done in order to get concrete and definite results. It's also that we have seen also in Shailesh and Sven's talk that it's hard to tell integrability or non-integrability from the training processes and how far the differences between a trained model, which is actually integrable, and non-integrable one, because they are basically one order of magnitude different. So it's not something that is so dramatic in this kind of scenarios. So the lax pair for the known case, the lax pair for H0 equals to 0 is this one. I mentioned that this is not a problem to write. And then what we'd like to do is, okay, first find expressions for these guys, for the Q non-zero and for the Q equals to 0 if you wish, but H non-zero, or in the general case. And then there's the entire, there's further the discussion of the R matrix and finding that indeed the currents that you construct with these operators are in evolution. So now you can think of complicating the things even more, similar analogously as taking alpha equals to 1 of alpha equals to sine B in the 2-dimensional case. And basically from your complications, you can pick up now a term that has an extra scalar field and a more complicated flux potential. You see that in the limit H0 equals to 0 in this picture, you recover some form of the analogous story. So it's like, nesting kind of models. Because if you kind of sort out things over here and you find the lax pairs, then you would be able to tell something about more complicated models as well. And yeah, I mean, this is a story essentially to be continued. And I hope to be able to report more about this in the future. But let me just summarize what we did and what we expect to achieve. So we have constructed a deformed Breitenlohner-Maison system that captures some integrability for a two-dimensional system in the presence of a cosmological constant or a flux potential. We are trying to look at this from a one-dimensional perspective, and we have posed the problem of constructing a one-dimensional lax pair in a machine learning amenable form. We have generated numerical lax pairs that, I mean, at least they are trainable, so they hint at the possibility of a lax pair rewriting for those cases. And then this will be complementary to the two-dimensional story. And analytical expressions are yet to be found, and then therefore symbolic regression techniques could play a big role in this adventure. So there are packages such as these Python packages for symbolic regression that were developed recently that could be maybe an avenue to build up analytic expression for the lax pairs in the cases that we have at hand. Okay, so that's what I wanted to tell you.
Thanks for the talk. So are there, yeah.
Yeah, thank you for the very nice talk. Again, on this last point, have you tried symbolic regression for the examples where you actually know the lax pair?
We have tried in Mathematica some hypothesis models with exponent. I mean, so this, I mean, there's not so much functional expressivity. So basically, you have just exponentials, and then you'd expect that this exponential pop up. So basically, we have taken combinations of power of exponentials. You have, I mean, if you look at, for instance, these guys, no? I mean, if you try to get a direct approximation from Mathematica or from, I mean, building this type of hypothesis models, then you find something, but it's not something that really tells you anything about the system that you're dealing with. So in that sense, I mean, they capture some of the features, but I mean, at least here, this is at a qualitative level, so to say. Then it would be interesting, for instance, if you could start with the exponentials directly or with the functions directly, and then try to rearrange them in a meaningful way in the lax matrices, for instance. But this is...
And did I understand correctly that in these more complicated cases, you don't even know whether a lax pair exists, right? So there you get some numerical results which minimize your loss function, and then, you know...
Exactly. And on top of that, these guys are 4x4 matrices, which, I mean, are not unique. I mean, you can even find more and more symmetries. Even if you see it here, you have this parameter lambda popping up, and for any lambda, you have a lax pair. So it's of course a difficult problem, but I'm sure something come up. Come on.
Thank you.
Is there any other questions or comments?
Sorry, we're not sure that the lax pair is or not. Do you know what the lax pair is? Yeah, so the equation is working for this. So in the ungauged case, can you have 4 on the slide? Okay. So by that it was and in the previous section of the talk, when we had the Breitenlohner-Maison like lax pair, they offer the same equation. So you know that there is a structure there. There is the question is whether you get find it in this bigger that.
Any other comments, questions? So what else do you expect to get from the ML? So here you hope to get the pairs, but so what will be like the aim of?
Well, yeah, that's a good question. So, I mean, in principle, what we'd really like to get are solutions of this type. So, I mean, solve for a BM system. And eventually being able to apply some of these ML techniques, for instance, to finding solutions at the two-dimensional level, right? So get the functional expressions for some of these guys. So, I mean, this is a first step in 1D that kind of, I mean, hopefully would complete the story, you know, the two-dimensional part with the one-dimensional part, and then make sure that everything matches. So at this level, this is a matching, but hopefully this can be extended to, I mean, and perhaps also due to these new and powerful symbolic techniques to construct actual deformations or new solutions in this cosmological constant or flux potential model.
So, and is it, I mean, how do you weight whether it's worthwhile or is it same difficulty to do it without the ML? So how do you weight whether it's worth to actually get into the ML?
That's a good question. So, I mean, building the solutions in these more complicated cases where you have some partial integrability is much harder than in the cases you saw before. So maybe again, this type of techniques would help you to like build some seed solutions, for instance, and then kind of combine both the analytical methods with the machine learning to say something about, again, the solution space.
Okay, so more questions or comments? If not, let's thank Damian again and remember